All right, Chapter 9, Problem 35. Suppose the hand in Problem 34 holds an 8.5 kilogram mass. What force F sub m is required of the deltoid muscle, assuming the mass is 52 centimeters from the shoulder joint? So this is a pretty straightforward one, more than a lot of the other questions in this chapter, but if we just draw our diagram here, we can see that if we'll have the joint here in the corner, so this is where the force on the joint is going to be. The muscle force is going to be just the next one over. Then we have the center of mass, and finally the weight. So just to talk a little bit about what's going on, a little bit more about what's going on in the picture, then we should say that the distance between Fj and Fm is d, between Fj and little mg is big D, and the distance between Fj and big mg is L. So in this scenario, we're just looking for Fm, like the question said, assuming we have this 8.5 mass. So we know this is 8.5 here, this big M. And essentially we should see that if we take this, just like in the previous, I'm not sure if you watched the last two questions or not, but choosing the pivot point to be somewhere where we don't know the force is most advantageous because, well, if we don't know the force, we can't really do anything, even if we included it in an equation. So it's best to put the pivot point here on the edge on Fj because we do not know what Fj is. So there's no way it can apply. If we put the pivot on top of the joint force, there's no way that it can have a torque because you need a distance to act on for a force to produce a torque. So with that, if we just take that corner as our pivot and counterclockwise as positive, so counterclockwise as positive, then Fm is going to be positive, little mg is going to be negative, and big mg is going to be negative, which is clearly what we see in our sum of the torque equation here. So I should also say that since it's in equilibrium, right, since the arm is not moving, or the hand is not moving, this essentially means that there's no angular acceleration and there's no linear acceleration. And so this means that we're allowed to say that the sum of the torques and the sum of the forces is equal to 0. We're just looking for Fm here, so this is just algebra at this point. You just add the two terms that are not with Fm to the left side, divide d sine theta, and plug in everything that you need. Plug in all the numbers you should need, which if you don't have them, then let's just say little m is 3.3 kilograms, big D is 0.24 centimeters, big M is, big D is 0.24 centimeters, big M is 8.5 kilograms, and then, this is L, I should include. The distance L is going to be 0.52 meters, and D is 0.12 meters. And then theta, I did not write as well, as 15 degrees. So with all of that, you should find that the F sub m, the force sub m is going to be 1600 newtons.